Hi all. Today we start discussing an exercise problem first. This is question number 27 of the exercise after Lagrange's interpolation. That is page number 1277. So this was the question. Given that sigma 1 equal 1 x equal to 1 to 10 f of x, sigma of x equal to 4 to 10 f of x, sigma 7 x equal to 7 to 10 f of x are given, and also f of 10 is also given. So using these facts you need to find out this f of 1. So that is the question. So using these quantities we need to find out f of 1. So the idea is you are given that this is summation 1 to 10 is this quantity. So once you get summation 2 to 10 f of x, if you will get the value of this, and by subtracting from this you can get the value of f of 1. Okay, so because this summation 1 to 10 f of x is nothing but f of 1 plus f of 2 plus etc f of 10. And what is the value of this? This is nothing but f of 2 plus etc f of 10. Okay, so once you take the difference between these two, you can get the you can get cancel these values, these two values. So you will get the value of f of 1 by taking a difference between these two. Okay, so our intention is to find the value of summation 2 to 10 f of x. Okay, so first of all we need to use Lagrange's interpolation formula for the same. So we first define a new function g of, we'll write it as g of y, or first of all we write g of some t. This is defined as summation x equal to t to 10 f of t, or f of x, sorry, f of t. So we write it as f of x again. So what is g of 1? So g of 1 will be summation x equal to 1 to 10 f of x. Okay, so you are given this value. What is this value? Similarly, what is g of 4? G of 4 will be summation x equal to, we need to replace this t by 4, so 4 to 10 f of x. And g of 7, g of 7 is summation x equal to 7 to 10 f of x. And finally, what is g of 10? G of 10 will be summation 10 to 10 f of x, x equal to 10 to 10 f of x. So this is nothing but f of 10 itself. Okay, so all these values are given. Okay, so as far as this g is concerned, we are given that the value of t and value of g of t for corresponding to the values 1, 4, 7, 10. Okay, so then this g of t will be, we will write it as in a table. So we write this is in a table. Okay, so we write the values of t and g of t in a table. So first of all we write this is 1. When this value is 1, then g of 1 is given, that is summation x equal to 1 to 10 f of x. So that is given as 500,426. And for the value of 4, the value 4 we have this one, summation x equal to 4 to 10, that is 329,240. And for the value 7 we have 175,212. And for the value 10 we have 40365. So these are the values of this function g. Okay, so we need to use the interpolation formula for this g, or to interpolate the value at 2. Okay, so we need to find out g of 2. Okay, so in order to evaluate this g of 2, we use first of all we write g of x, or interpolation formula for this g of x. How will you find out g of x using Lagrange interpolation formula? So we consider this as these values are y0, y1, y2, y3, and these values are say some t0, t1, t2, and t3. So we use Lagrange's formula as y0 times the Lagrange's formula is x minus t minus this t naught. We write this t minus t naught first, then not t naught, that is first one is t1. So the first one is t1 here. For Lagrange's formula we write this is t minus t1, t minus t2, t minus t3 whole divided by t naught minus t1, okay, t naught minus t2, and t naught minus t3. So this is the first term, and the next, sorry, this is not g of x, this is in fact g of t. We need to write the explicit formula for g of t instead of g of x, and y1 times the next will be t minus t naught, t minus t2, we avoid t1, t minus t3 whole divided by t1 minus t naught, t1 minus t2, t1 minus t3, and the next two terms are y2 times t minus t naught, t minus t1, t minus t3, we avoid t minus t2. So in the denominator we have t2 minus t naught, t2 minus t1, t2 minus t3, we avoid t2 minus t2, plus y3 times t minus t naught, t minus t1, t minus t2 divided by t minus t3 minus, right, t3 minus t naught, t3 minus t1, t3 minus t2. So these are the terms in the Lagrange's interpolation formula. So using this formula we write g of 2. We need to evaluate g of 2, and so we need to replace all the t by 2 and corresponding values for x, y0, y1, y2, y3, and t0, t1, t2, t3. So the first term will be 5 0 0 4 2 6, that is y0, times, we need to substitute the values for this, so that will be 2 minus 4, 2 minus t2 is 7, 2 minus 10 divided by the denominator will be this is t naught is 1, then 1 minus t1 is 4, 1 minus 4, 1 minus 1 minus 7, and 1 minus 10. So this is the first term, plus y0, and we replace all the values of this y1, y2, and t1, t0, t1, t2, t3. Okay, then we will get, so these are the values obtained by substituting the values for y0, y1, y2, and so on. So first of all we then now we simplify this. By simplifying, you can get this is equal to the value 5 8, sorry, the value, the whole sum will be 4 4, right, this value is 4 4 1 5 8 2.432. So this is the value obtained for this g of 2. Now we can write what is f of 1. F of 1 is g of 1 minus g of 2. Okay, what is g of 1? G of 1 is summation 1 to 10 f of x minus summation 2 to 10 f of x. Okay, so this is g of 1. G of 1 is given, that is 500,426 minus g of 2 is this one, 441582 0.432. Now by taking the difference of these two, you can get 58843.57 or 0.6. Okay, so this is the value of f of 1. Okay, so this is the way we use the Lagrange's interpolation formula to evaluate f of 1. Okay, similar problem is discussed very next to this question, so please try to find out the value of or solve that problem. Okay, now we continue discussing our the solutions of the methods for finding the solutions of algebraic and transcendent equations. So this is the last class we have discussed iteration methods. This is its consequence. It's called Newton's iteration method or Newton-Raphson method. Mostly this is known as Newton-Raphson methods. Okay, so we if you take the first approximation x naught as the approximate root, that means if you have a real root alpha in between some a and b, then you can take one of these values as the initial approximation. So once you obtain this initial approximation, you can evaluate the iteration formula as xn plus 1 is equal to xn minus f of xn divided by f dash of xn. Okay, so this is the iteration formula. This is the values for n is equal to 0, 1, 2, 3, etc. So and this where this f of x equal to 0 is our required equation to find the solutions of this equation f of x equal to 0. We need to perform this iteration. Okay, so this is what we called a Newton-Raphson formula or Newton-Raphson method to evaluate the solutions of approximate solution of the transcendent or algebraic equation. So now once you understand this formula, we have three remarks. The first one is the geometrical interpretation of this formula. Okay, interpretation. What is the meaning of this formula? To get the geometrical interpretation, so you consider this function y equal to f of x, and alpha is its corresponding root or 0, this is actual 0. So if you take the first approximation as x naught, then this point can be denoted as x naught comma f of x naught. Now you consider the tangent at this point. Okay, so this tangent meet at this point, and how do you get this this point? That is the first thing, and this point is considered as our x1. So how will you get this x1? So first of all, you need to write the tangent of this this curve at this point. Okay, tangent of y equal to f of x. So that is obtained by y minus y naught, equation of the tangent. This equation of this line is obtained by considering the line passes through this point x naught f of x naught. This is nothing but our y naught, so it passes through x naught y naught. Then the equation of the line will be f of y minus y naught into slope into x minus x naught. Then what is the slope? Slope is the derivative of f at this point, so the f dash of x naught, that is the slope here. So this is slope of the tangent at this point. Okay, so now this f of this y naught is nothing but f of x naught. Okay, so y minus f of x naught equal to f dash of x naught times x minus x naught. So this is in fact the equation of the tangent of this curve y equal to f of x passing through this point x naught f of x naught. Okay, so in order to get this point, we need to put y equal to 0 here, because in order to get the point of intersection of this tangent and x-axis, that is obtained by y equal to 0, because at on the real line we have y equal to 0. So when you put this value y is equal to 0, then this takes the form minus f of x naught is equal to x times f dash of x naught minus x naught times f dash of x naught. Okay, so this is the value of x1 is this, so we need to replace this x by x1, then you will get you can easily get x1 from this equation. This x1 will be we can solve for this x1, then that will be x1 times f dash of f naught f dash of x naught equal to, this will be equal to x naught times f dash of x naught minus f of x naught. Okay, so this x1 will be x1 takes the form x naught minus this f of x naught divided by f dash of x naught. So using this equation, using this value of x naught, you can get the value of x1. Okay, similarly you consider x1 here, and you can get the point x1 comma this point is x1 comma f of x1. Then using the same argument, you can get by considering the tangent here, then this point will be x2. Okay, so the x2 takes the form x2 is equal to x1 minus f of x1 divided by f dash of x1. So we can generalize this formula as x of xn plus 1 is equal to xn minus f of xn by divided by f dash of xn. Okay, so this is the geometrical interpretation of this this Newton-Raphson method. So when you repeat this process, you can get the or these values x1 x2 converges to the actual solution, so that will give the real solution for this equation f of x equal to 0. In the next remark, we will discuss the rate of convergence, or the condition for convergence, or you can write it as a condition for convergence. So for this we write it is not right, it is condition for convergence. This is the condition for convergence. This is obtained using the previous method, iteration method, such that mode phi of x is less than 1. So using this fact and this, when we consider this as our phi of x, then you can get this form, this condition. Okay, so this is the second remark, and finally we have the third remark, that is nothing but the rate of convergence. Okay, this is the condition for convergence. Next we will consider the rate of convergence, and that rate of convergence is defined as that is half, that is rate of convergence, in terms of this f and the derivatives of f, you can get the rate of convergence. Then rate of convergence is defined as half this k times epsilon m square, that is nothing but half of f double dash alpha divided by f dash alpha times epsilon n square, that is epsilon n plus 1, where this epsilon n plus 1 is the error in the n plus 1 stage, that is the difference between alpha minus xn plus 1, that is the n plus 1th approximation, and difference between the actual roots and this n plus 1 approximation. Similarly, epsilon n is alpha minus this xn. So this is the rate of the convergence. That means the error follows this rule. That is the meaning of this. So this is the its rate is the subsequent rate will be the constant times. This is always fixed. This is independent of n. So this constant times epsilon n square. So this is the previous error. So the subsequent error will be the square of the previous error. So this is this Newton-Raphson method has a quadratic convergence. In other words, we can say its order of convergence is 2 due to this factor. Okay, so this is 3 remarks on this Newton-Raphson method. Now we will discuss a problem which illustrate the Newton-Raphson method. So this is the example. Find the real root of the equation x raised to 4 minus x minus 9 equal to 0. So first of all, we need to get the initial approximation. So first we evaluate f of 1. You just evaluate f of 1, then you will get the value as minus 9. You can cancel first two terms, 1 minus 1, that is 0. And next we evaluate f of 2. F of 2 is a positive quantity, that is 5. That is 16 minus 2 minus 9, that is 5. Since this f of 2 is less than the also f of 2 is we can consider this f of 2, the modulus of f of 2, that is 5, which is less than modulus of f of 1. You can get you can take the initial approximation or first approximation as or x1 or x0 as 2. So using this Newton-Raphson method, we evaluate x2. For that we evaluate f dash x. What is f dash x? That is 4x cube minus 1. Okay, so this is the derivative of this function. Now you evaluate x2. How do you evaluate x2? The formula is x2 is equal to x1 minus this f of x1 divided by f dash of x1. Now you substitute the values for this x1 and f of x1. You can get this x2 is equal to what is x1? X1 minus, we write the first, we evaluate the formula that is x1 minus this f of x1. F of x1 is obtained from this x1 raised to 4 minus x1 minus 9. This is f of x1 divided by f dash x1, that is 4 times x1 cube minus 1. Okay, now you can simplify this, that will give 3 times x1 raised to 4 plus 9 divided by 4x1 cube minus 1. 4x1 cube minus 1. So now substitute the values for x1 and x1 in numerator and denominator. You can get that is 3 times 2 raised to 4 plus 9 divided by 4 times 2 raised to 3 minus 1. That will give the value is 57 by 31, that is 1.8. You can evaluate this using a calculator. So you will get the second approximation x2. So using this x2 you can evaluate x3. Then you will get x3, use the same procedure. So x3 will be, you can get x3 will be 1.881 and x4 will be 1.813. Then x5, the similar fashion you can evaluate x5 using x4. So that that will be that quantity is again the x4 will be 1.813. So from this you can write the you need not worry about x5, or you follow this procedure and try to find out the solution correct up to 3 decimal place. So you continue this process, and if you got to consecutive approximations for which these first 3 places are the same, then you can conclude with that answer. Okay, so this is the value of this is the root of our function equation f of x equal to 0. Okay, so this is the way we use the Newton-Raphson method to evaluate the roots of the equation. Thank you.